I hope that you can investigate more about energy in industry. Okay, try to investigate what cases, and then you can make a video on it. Okay, thank you very much.
Kalau energy selalunya dia ada fan tu, air penetration. Fan ni dia nak check cracking, macam crack kat surface column. Kita tak nak run column tu crack tapi kita tak tahu. So masa EA tu, apa lah, kita pun check column tu lah. Dia ada crack lah, dye fan tu. Macam betul-betul kita sembuh chemical lah. Lepas tu dia akan bertak. So kita nampak lah, kalau crack dia nampak dia dye fan. Lepas tu ada banyak lagi, ada eddy current,
If an alternating voltage is applied to the coil, the effective current through the coil is much smaller than when applying direct voltage. The reason for this is the alternating magnetic field, which generates a counter-voltage in the coil by self-induction. The counter-voltage in turn reduces the current consumption. Pushing an electrically conductive tube through the coil increases the effective current significantly. This is because the alternating magnetic field of the coil induces a current in the tube in circumferential direction, the eddy current. The eddy current in turn generates its own magnetic field, which counteracts the magnetic field of the coil. Consequently, the self-induction is low and the current consumption high. When a defect, for example a crack, comes into the path of the eddy current, the current consumption of the coil drops. The eddy current has to flow around the defect. The path of the eddy current is now longer, and the electrical resistance of the eddy current circuit is larger. This leads to a reduced magnitude and a reduced magnetic field of the eddy current. The self-inductance of the coil is increased, and the current consumption decreased. In practice, the alternating current frequencies are not as low as shown here for demonstration. They are much higher, typically in the region of some kilohertz. From now on, we're going to omit the magnetic field lines in the animation and represent the eddy current in a simplified static way. This technique can be improved considerably if not only a single coil, but several coils are used. The original coil, which is now called the excitation coil, is supplemented with the receiver coil on the left side, and a receiver coil on the right side. A voltage meter is connected to each of the receiver coils. The animation once more shows the physical background. The current consumption is high in an area where the tube is intact. The reason for this is the undisturbed flow of the eddy current. Because the magnetic field of the eddy current doesn't flow through any of the two receiver coils, we measure virtually no voltage on them. As soon as the excitation coil reaches the left end of the longitudinal saw cut, the current consumption decreases. The reason for this is the longer path of the eddy current. Because the eddy current now flows partly underneath the right receiver coil, its alternating magnetic field induces a voltage there. When the excitation coil reaches the right end of the longitudinal saw cut, the eddy current partially flows under the left receiver coil and induces a voltage there. Still further to the right, near the saw cut in circumferential direction, the eddy current is undisturbed. Its alternating magnetic field flows neither through the left nor the right receiver coil. The voltage meters indicate almost nothing. The technique can still be further improved if we use only one voltage meter, which is connected to the right-hand terminals of the receiver coils, and if the left terminals of the receiver coils are connected to each other. The voltage meter now indicates the difference of the voltages induced in the two receiver coils. We have set up this test arrangement in the laboratory too. The voltage meter clearly indicates the ends of the longitudinal saw cut. Unfortunately, even this arrangement cannot detect the saw cut in circumferential direction. We can achieve a substantial improvement with this layout of coils. The excitation coil remains unchanged. The right receiver coil is wound in the form of a capital D and sits within the excitation coil. The left receiver coil is laterally inverted. We switch the receiver coils against each other and only measure the voltage difference between them. Now everything works in a way that suits us. Small voltage difference in the intact sheet, strong voltage fluctuations at the left side of the saw cut, and at the right side. But one point should always be kept in mind. The two D-shaped receiver coils must have the correct orientation for saw cuts and cracks. Otherwise you measure only little or nothing at all. If the orientation of cracks is not known, the probe is rotated by 90 degrees after the first pass and the test piece is scanned a second time.